Gentlemen, and welcome to the Kawazi conference call. My name is Maria, and I will be your coordinator for today. At this time, all participants are in a listen-only mode, and we will conduct a question-and-answer session toward the end of this conference. If at any time during the call you require assistance, please press star followed by 0, and a coordinator will be happy to assist you. As a reminder, this call may or may not be recorded. I would like now to turn the call over to Mr. John Duncan, Project Manager.
Thanks, Maria, and welcome everyone to today's Cyberseminar given by Jeff McDonnell at Oregon State University. Just wanted to quickly remind those of you who have participated before and bring others of you up to speed about this WebEx format. If you have any problems, you can send those to me via the chat window, which is in the lower right-hand corner. You can select all participants if you want to send a note to everyone, or just the host, which goes directly to me or anyone else in the room. It would be very similar to whispering in the back of another seminar. We're always anxious to get feedback on these cyber seminars. That can be done by sending an email to me at commanager@kawazi.org. And this presentation will eventually be available for download. I had some problems earlier today, but it will be up there later this afternoon or early tomorrow. So the rest of this semester, actually the rest of this month, is going to be great. After Jeff's talk today, we've got a full month of Friday lineups here. Effie Fufula and Chris Paola from NSAD will be giving introduction and background on everything they've got going up there in Minnesota. Manu Lal will be giving a vision paper presentation on hydrologic change detection. And then the last Friday of this month, David Maidman at UT Austin will be giving a status report on the HIS effort. So all of this information is up on the website, and the presentations will be there for download. So today, we're very happy to have with us Jeff McDonnell, who is the Richardson Chair in Watershed Science at Oregon State University in the Department of Forest Engineering. His PhD is in forest hydrology, and he's a registered professional hydrologist with the American Institute of Hydrology. Jeff has been heavily involved in IAHS and the PUB effort in particular, which he will be leading a workshop in January of next year. So although the link is up there now, more details will be up on the Kawazi website about that workshop in Berkeley, California in January, sometime early next week. So details are soon coming on that. So keep an eye open for that. But Jeff, we're very happy to have you with us today, and you have a slight change of title, so I'll let you describe that and look forward to hearing your presentation.
Okay, well, thanks very much, John. It's a pleasure to be here and to give this talk. Many friends and former students I see logged in, so it's great to be able to come and speak to you. I know the title that was advertised for this talk has changed. The original talk was really oriented towards reporting on a vision workshop that we held here at Oregon State about a year and a half ago. For information on that workshop, there's a website you can get to via my website, and I think there's a talk or two that I've given previously that's both at the Kawazi website and on the Vision Workshop website on my website as well. So today I've heeded the original title, which was Moving Beyond the Theory Impasse, and I've personally moved beyond this theory impasse and wanted to give a talk on the dialogue between experimentalist and modeler. And this is an outgrowth of discussions at that workshop, but represents more some of the things that we're doing here in my group at Oregon State. So I'd like to acknowledge my what should be probably PhD students and postdocs that I've had at OSU in the last few years that have gone on to other places, and you'll be hearing about some of their work. Nick Hirt now at SLU in Umeå in northern Sweden, Mario Martina at Bologna, Brian McGlynn now at Montana State, Kevin McGuire at Plymouth State, Jan Seibert at Stockholm University, Ilya Trump van Meerveld, who's at ETH Lausanne, working with Mark Parlange, Tara Uchida, now with the Ministry of Works, Kelly Vacher at Eason University, and Marcus Weiler at UBC. So what I'll be talking about are ideas that have developed over the last few years with these colleagues now, and I want to acknowledge their contributions, and you'll see some reference to their work as we go through. What I'd like to talk about for the next hour or 45 minutes or so are some issues relating to this dialogue between experimentalist and modeler. Are the main problems and maybe what's the status quo in this regard. We'll review what the past couple of decades have revealed then in terms of paradoxes, some puzzlements that still, I think, defy process description, and some patterns that we see. Examples of how we might improve the dialogue, and some of the things that we're trying here at Oregon State, and others, of course, are trying, to try and use experimental evidence to structure, test, and most importantly, as you'll hear kind of permeate the talk, how to begin to reject models, and then looking ahead. This model rejection, I think, is the thing that the experimentalist is interested in most, and we'll try to talk about this a bit, also in the context of PUD, this new IAHS decade on prediction in ungauged basins. Now, what I'm going to talk about is nothing that others haven't already talked about. In fact, a great paper was by Tom Dunn in the early 19th line, this problem of lack of dialogue between experimentalist and modeler. And I like this quote from the paper where he talks about the need to refine runoff concepts and combine field experiments with realistic, physically based mathematical models. And I think the things that Dunn said in this 83 paper are just as relevant, unfortunately, today as they were in 1983. I don't think we as a community have really heeded his remarks from back then. Of course, the status quo in terms of applied hydrology is to develop models that are designed to predict perhaps a 1 in 50 year event, you know, looking at, for instance, a flood wave or for design purposes. This is based largely on infiltration excess, Horton overland flow theory, and getting the water to the stream for the right reasons isn't so important as simply making a useful prediction for design characteristics. But when we're interested in things like climate change, land use change, or maybe using a hydrological model as the basis for something that will deal with also water quality, we really need to question the status quo, because often we're assuming things that we know not to be true. For instance, what we're all taught in Hydrology 101 in an engineering hydrology class in terms of graphical separation of hydrographs into what might be considered quick flow and delayed flow, we know this is not the case based on the components of flow that have been revealed through isotope and chemical-based tracer studies over the last many years and even decades. Now, we have learned a lot since the first international hydrological decade. What we think we know now is really built largely upon variable source area theory that came not only from Hewlett, and by the way, we're having a tribute to John Hewlett session at Fall AGU. He passed away last summer, and this session will try to chronicle his lifetime achievements. But his thoughts have really influenced the way that our current generations of models have developed and our current concepts in runoff generation have developed. And we all know about this combination then of expanding surface saturated areas around the stream channel and in the heads of the smaller order channels in response to a rising groundwater table. And then in steeper terrain, this can be matched or even exceeded by subsurface storm flow from the hill slope. Now, one part of then this variable source area is what was defined in some benchmark papers by Dunn and Black in the early 70s, saturation excess overland flow. So this is the rapid overland flow portion of this, and I'm showing a diagram of this. And this cartoon on the left-hand side we see in many textbooks. So this is, I'm trying to review now maybe our current status quo understanding of some of these processes. And then subsurface storm flow as revealed by a number of benchmark studies in the UK and elsewhere in the early mid-1970s. And we've had many studies over the years that have looked at varying combinations of lateral flow through the soil matrix, through different soil layers, and preferential flow through hill slope scale preferential flow features. And more recently, the role of bedrock in contributing to runoff generation has been examined, especially in steep Pacific Rim sites. Now, the way all this has come together, I would say, is that we have a model out there that's widely embraced by the hydrological community top model, and this encompasses then this variable source area theory. And this captures many of the things the National Hydrological Decade have observed, the expansion and contraction of surface saturated areas, the use of topography as a proxy for flow path, where the topographic index is used as a way to route water laterally in the catchment, and depending on the steepness of the terrain, water moves via subsurface storm flow or saturation excess overland flow, depending on the characteristics of the local basin. But you might say that these top model assumptions that I'm showing here are really now the dogma in the field, and are really maybe where the experimentalist and modeler are starting to come together. So these assumptions are that water table is mimicking the soil surface topography as shown in this first upper left-hand corner plot. So we use Dupuy-Forchheimer to kind of think about water table flexing up and down across the catchment in a steady state-like way. This topographic index, where A is the upslope contributing area and beta is the local slope angle, gives us now an index of moisture variability and flow path direction, given that elevational potential dominates total potential in steep terrain. Terrain then is a very good predictor of flow when it's steep, and of course increases in a downslope direction. Another assumption is that the water table depth to water table is greatest near the divide and would be 0 at the edge of the variable source area. And then finally, this exponential decline in hydraulic conductivity or transmissivity, if you like, with depth. So this, I would submit, is our status quo. What I'd like to do now is talk about maybe what we've learned since 1983, when Dunn published this quite important paper on the dialogue between experimentalist and modeler. And the first thing we might think about doing is rejecting the top model assumptions, all of them. I know this is a bold statement, but I want to be thought-provoking here as I can, just for a minute. But I would say that what the last 20 years has revealed is that we need a new theoretical framework for how we understand the runoff process if we want to build models that capture the dominant processes in different environments, and we build model structures that maybe aren't one-size-fits-all, but we can modify slightly to capture the dominant processes in any given terrain. So what I'll do is go through maybe each of these assumptions and challenge them with some recent data that we've been collecting, and then talk about how this might inform this dialogue between experimentalist and modeler. So first, this idea that steady state is a good assumption. The notion that the water table is flexing up and down across the domain. Here's some data from Sparkforget, a site, and this is where Kevin Bishop did his PhD some years ago, and we've been looking at the relationship between water table and runoff. This is from a well in the variable source area, and this is showing actually quite a tight relation between water table fluctuations and runoff. And these are a series of measurements for many, many storms, showing you this tight relation, highly nonlinear. This is a result, of course, of hill overlain by more transmissive mineral soil. So as water tables rise into more transmissive soil, you get a rapid increase in runoff. The Swedes call this transmissivity feedback. But if we start moving up the hill slope, this relationship that's so nice in the riparian zone begins to break down, so that by the time we're up towards the ridge, the water table is really behaving independently to the runoff. These data would challenge, I think, the steady state assumptions that are widely used in many of our models. When we trench our hill slopes, and last week we had a first slope intercomparison experiment called SLICE at the H.J. Andrews. We had about 40 participants from around the world come and compare our different trenched hill slopes. And I think from that experience and from the recent data published over the last few years, subsurface storm flow is not what we thought it was pre-1983. Several studies, not just this one, have shown how subsurface topography, not surface topography, might be the dominant control on the distribution of mobile water in the subsurface. This happens to be from the Panola site just outside of Atlanta, Georgia. And here you're seeing a topographic map showing fairly planar surface topography, and then the underlying bedrock topography at the soil saprolite interface in this case. And what we find at this and other sites that are like it, where there's a way of a permeable soil over a less permeable bed, is that often most of the flow is correlated with the subsurface topography. That's because when these hill slopes do turn on, water is backing up at that soil-bedrock interface and then following the lower surface. And this is showing a topographic index calculation on the left side for surface topography and the right side for that bedrock topography I showed in the same slide. So what we have are fairly network-like, rather narrow ribbons of mobile flow with very, very high anisotropy. So things much more rapid, able to transmit a flux of water and particles in the lateral direction than vertically. And mobile water in these higher kind of mobility flow paths, Doug Burns has shown that these are often dilute and base cations, reflecting the flushing frequency of these zones, given that the weatherable products are stripped over time. Let me just give you an example. Those previous two slides I may have shown before, this is work of Ilya Tromp van Meerveld at the Panola site. Here we've reactivated some of the instrumentation that we had in the late 1990s, just to take a look at an example of this kind of behavior. That's a diagram or a photo of the slope, which is fairly well instrumented now, including looking at transpiration and all the inputs and outputs and changes in storage on this hill slope. So here's the Panola Hill slope, the same one we were just looking at. We're going to look at a number of rainfall events of different size, and I'll be increasing the event size as I go through. Here's the hill slope outline. We're looking at it in plan view. The dots represent wells, either maximum rise wells. So I'm not talking about the dynamics right now, just whether or not we detected saturation at the soil-bedrock interface. So whether or not we detected any perched water. So there's a 5 millimeter event. Those are those blue patches are where we had some water table develop. A 9 millimeter event, getting some other water table developing. 16 millimeters. These events are all in 2002 during Ilya's PhD field season. 50 millimeters, you're noticing still we have yet to maintain a connection to the downslope end where we have a trough or a trench and we're collecting subsurface storm flow. Now at 59 millimeters we see a connection and we see some network-like connection to the base of the slope and now a 61 millimeter event. So if we look at the net effect of this kind of pattern, we see that here in this diagram on the right. Here's flow on the y-axis versus total storm precipitation, and each one of these dots then represent an individual rainstorm. About 55 or 60 millimeters of rainfall before we get any lateral subsurface flow emerging from the base of this hill slope. So this kind of connectedness is a precondition for subsurface storm flow, and subsurface storm flow itself is highly threshold-like. What this is also suggesting, I think, is that this is almost like an emergent property of the hill slope. So rather than focusing on the processes at any given pixel on the slope, like we often do, what we're saying is maybe there are some ways to look at the hill slope in a more holistic way. This is what we might call a fill and spill process or analogy. I spent the summer in Sweden. This is a postcard from around the Uppsala area. And just imagine this roadway with half a meter or a meter of soil on it. These are pockets of saturation that develop, and it's only when these pockets of saturation become connected that we begin to see flow down this roadway. Well, we do see this in various areas, and these effects are very clear. As a small joke, this slide somehow got corrupted in the process here, but we're looking at flow on the y-axis, again, versus precipitation on the x-axis. And these lines, these thresholds and then the slope of the line, these are from 4 different hill slopes that we've trenched in different parts of the world. The red line is Mai. The black line over here on the right is Panola, the one you've already seen. The blue line is the H.J. Andrews, where Kevin McGuire has done his PhD work recently. And then the green line is a site in Japan. Again, showing that while the thresholds themselves might be different, and even the slope of the line after the threshold could be slightly different, if we think of this as an emergent property at the hill slope scale, each of these are showing the same kind of behavior. This is rather different to our status quo descriptions, I guess, of hill slope hydrology. The other thing is that in each of these slopes and others that we measure, and this was quite true at the slice workshop last week, pipe flow seems to dominate this lateral flow. So when the hill slope does turn on, if you were able to individually or plumb individual pipes, these are laterally oriented for the most part macropores, often in the lower parts of the soil profile, this pipe flow represents a fairly large proportion of the total flow. So here's Panola, this is the pipe flow on the y-axis and total flow on the x-axis, and the one-to-one line is shown here. Some of these are quite a large proportion of pipe flow. So these are some of the things that we're finding at various hill slopes. I'm going to skip this slide. Somehow it got lost in translation. But we see these different parts of the watershed contributing in fairly threshold-like ways, where we've talked about these as being kind of like cryptic reservoirs, to use Rick Hooper's term here, where different parts of the watershed are contributing at different times of the hydrograph. Here are some data from Doug Burns, PhD, showing sodium sulfate concentrations from Panola. This is the stream concentration where my red dot is. I hope people can see that. At the beginning of the event, this is the rise of the hydrograph, and this is the trajectory of the stream chemical composition, bounded by these extreme concentrations, which are the end members. Here's the hill slope, the riparian groundwater, and in this case, a bedrock outcrop. This is an event that was in excess of 60 millimeters of rain, so the hill slope was turned on, but you can see is not so well expressed in the stream chemistry. It's dominated by riparian groundwater and a large amount of outcrop water. So these, we might say, are units of the catchment that are contributing in fairly threshold-like ways, and we see this expressed at the catchment scale also. That's one of the most important findings in the field generally in the last 2 decades since Dunn 83, was this finding of old water dominating flow in the channel even during large events. My last cyber seminar was on the old water paradox. I'm not going to repeat that material here, but I think Jim Kirshner has done a really nice job at clearly articulating this problem in a way that the broader community has appreciated. And that is, if we have water flux, these are data from the H.J. Andrews from Kevin McGuire's PhD. We're looking here at water flux rainfall runoff relations. The blue bars are the rain hydrographs. The red or darker red lines are the stream hydrographs. We see where certainly rain amount, intensity, duration, antecedent wetness affect the nature of response, but when we see rain, we see some type of runoff response. However, when we look at something that's carried with the rain, in this case, oxygen 18, that's part of the water molecule added naturally during rain events, here we have a similar kind of noisy input, just like we have in our kind of spiky rain input. Now what's carried with the rain, as expressed in the stream channel, is very lagged and damped. So this is what's carried with the water. This is more the pressure wave movement of water through the system. This suggests that hill slopes store water for months to years and then release it in minutes to hours to the stream. Now, some have called this a paradox. I think if you look into the recent process literature, it's not so paradoxical, but it's a great way, I think, to draw attention to this as a fundamental property of watersheds that we see in various parts of the world. If we look at how this might be expressed, that last slide, I should just pop back here. This is over a period of some years. So this is 2001 to early 2003. Now let's look at an event. Here's an event, again, from Kevin McGuire's work. This is watershed 10, a research watershed at the H.J. Andrews. This is a trenched hill slope. And what we're looking at here is the input. This is the rain amount, and then the O18 of the rain. In the lower portion, this is the hydrograph from this small watershed. Watershed 10, this is where Dennis Haar worked in the late 70s, probably one of the most responsive headwater catchments documented in the literature, and yet most of the water, even in this super steep, wet, responsive basin, is water that existed in the basin prior to the event. If you trench the hill slope and we look at subsurface storm flow, despite the fact that we have very, very high rates of water flux through those soils, most of the water is pre-event in origin, if we do a very simple separation into those two components. Now, again, thinking about our current situation, if we're a modeler, we have to deal with parameter identifiability, model uncertainty. By that I mean, here's an example of a modeled hydrograph. Runoff on the y-axis versus time, you're seeing a number of events, and you see predicted and observed, and you might look at that and say, wow, the model's working very well. We've got a high R-squared or a very high Nash-Sutcliffe efficiency measure. But what we know from the work that Keith Bevan has done at Lancaster, the group at Arizona, and many other groups are working on this, is the identifiability of parameters within the model is difficult, and we could have a whole slew of similar good fits. If this is the efficiency of that hydrograph fit that you saw on the previous slide, we can have that same high efficiency, whether you think of this conceptually in an R-squared or Nash-Sutcliffe efficiency way, just for the sake of argument right now, but we could do it for very different, for instance, in this case, hydraulic conductivities. So we can turn the knobs in different ways and achieve the same fit and be right for the wrong reasons. Many groups are studying this on the modeling side. What I'd like to add is that for models that include flow paths that are in some way realistic, if we're going to address problems of land use change, water quality, climate change in our hydrologic models, we also need to confront this. Here's discharge efficiency on the y-axis for that same plot, and now we're looking at the mean residence time. The model, in this case, this is a run from the Maimai catchment where we have very short residence times at about 120 days out here. This is illustrating, I think, the problem that we face when we begin to think about bringing water quality realistic flow paths into a traditional hydrological model. That is, we can get good fits for discharge through calibration, but we are not able to, at the same time, get realistic residence time estimates, which residence time would be out here around 120 days. Conversely, we can get more realistic residence time estimates, but when we look at the efficiency for discharge, we're really quite poor. This is part of the problem, and this is where the dialogue between experimentalist and modeler, I think, can be most improved. So I'll spend the next few minutes talking about how we might improve the dialogue, giving just a few examples here at Oregon State. And I love this quote. Not so much the things that we don't know that get us in trouble, it's the things we know that ain't so. And I'd argue that what I'm talking about in a process mechanistic sense are things that we know as an experimentalist community. It's just that we ignore them, and we might argue to our peril in our watershed models. Now, I think for starters, the first thing an experimentalist would say is that, you know, we need to change the whole philosophy in our physically based models because the catchment is not this collection of soil cores. And this diagram from Jan Hopmans at UC Davis, I think, is a great kind of illustration of the current problem. We take a soil core, we bring it into the lab, we characterize it for weeks or months. We have such incredible knowledge of this soil core, but we're always forced to use our subgrid parameterization, Darcy Richards as our subgrid parameterization, and the catchment doesn't behave as this collection of soil cores. We know from our work that hill slopes are operating in a very threshold-like way. There's hysteresis in the catchment. There are different catchment positions that are controlling different behaviors and different drivers to water flow. And this is also a PUB problem. PUB is really the second international hydrological decade, and the aim of PUB is to develop new generations of models that aren't so beholden to calibration, and so we reduce calibration and we increase the use of models that are based on understanding. I think the problem is that the first international hydrological decade was a double-edged sword. It resulted in the gauging of 6,000 or 7,000 basins worldwide, but now we're held hostage to needing that data to calibrate our work in a predictive mode. What we really want to do is develop sufficient process understanding so we can move beyond calibration, and that's, I think, in a nutshell, what PUB is about. So trying to reduce predictive uncertainty, although predictive uncertainty could actually increase as our understanding improves, but maybe what we really want to do is reduce the need for calibration. Because right now, as Siva Palin has said often in his recent papers, calibration is, grist for the mill in terms of our uncertainty of how these processes work. So we deal with our uncertain understanding of process through brute calibration. Now, one of the things we've tried is to think about how we might use soft data. That's data from the experimentalist that's maybe pretty fuzzy. You've gone out into a catchment for a week with a grad student and a technician, and you've made some soil depth measurements. It's tough to spatial map to the modeler to use perhaps as a check on the model, but the modeler might develop evaluation rules that the experimentalist could fill in based on her or his understanding of how the catchment might work. And this is a way that one might use, say, some kind of fuzzy membership function, where let's say with the soil data or soil depth data, during that short period of time, you may not have dug any soil pits that were less than 1 meter or deeper than 3 meters. You're pretty sure that in this area, based on your knowledge of the geomorphology, there's nothing greater than, say, 5 meters depth, and you don't see any bare outcrops, and you might guess that soil wouldn't be less than 25 centimeters. Very fuzzy, very qualitative, arm-wavy information, but highly useful in terms of constraining parameter ranges and evaluating and testing the model. Another way is to perhaps look at our parameters in an a posteriori way with some very soft or fuzzy understanding of how a basin might work. This is some work from Kelly Vachey's PhD work. Here's model efficiency or parameter for different parameters in the model. This is a shape parameter for the depth decline of hydraulic conductivity, porosity, effective hydraulic conductivity, and initial saturation in the model. And this is showing efficiency on the y-axis. Here are these classic dotty plots. And I want to just show how perhaps some knowledge of the percent of pre-event and event water could be used to reject maybe the nonsense dots that populate this dotty plot. This is for a poorly gauged watershed in Chile, and we're going to use as our a posteriori parameter rejection tool just percent event and pre-event water. So an experimentalist might look at these data and say, well, I know this area to be a variable source area producing zone, therefore I would expect the percent of bird water or pre-event water to be more than 50% at the peak of the hydrograph, and the percent new water to be less than 50%. It's likely much more pre-event water than 50%, but let's just start with that as a very conservative approximate number. Well, we can immediately see where some dots are producing results for the wrong reasons, according to the experimentalist. So this is, again, trying to engage the experimentalist in model evaluation, maybe in a slightly non-traditional way. So what I'd like to end with is an example that maybe takes us towards thinking about more orthogonal measures for how we might structure models, how we might improve models, and ultimately reject models. Now, it's not, these measures aren't orthogonal in a statistical sense, but they're bringing in different, non-redundant information to the model testing evaluation. So I'm saying that discharge, which is really the type of data that we use almost exclusively in our model calibration and evaluation, probes one space. Stream water residence time really probes a different space. And there's been a lot of work recently to show that these two really aren't related. These are separate types of information. One clocking the particle transport through the system, as Jim Kirshner would say, and one more the pressure response through the system. And we're also, in this case, going to look at soil water residence time. So I'm going to give a quick example of this to try to illustrate maybe how we might improve this dialogue. Now, just a little bit on the technique. I'll only show this one slide. This is from Kevin's work. We're really thinking of the catchment now as a filter. So we have our rainfall input in terms of O18 or precipitation input, and the catchment is a filter that results in a lagging, damping, and smoothing of that input. So this is now the stream flow or base flow response that we might see to this input. So the catchment is a filter, and the catchment, of course, has a range of flow path characteristics from short to long, from young to old, and we can express that as a function. One of these many types of functions could be an exponential, could be a dispersion model, could be two parallel linear reservoirs. Anyway, this function then says something about the flow path heterogeneity in the basin. Now, there's a fairly extensive literature on this. I'm not going to go into more detail, but I'm going to be using this technique to define some of the resonance times that we'll use in our model structuring and evaluation in just a moment. So what we do then is we choose a function that gives us the best fit between input and output. We make an assumption about how much of the precip formed groundwater recharge, and we're able then to compute using a convolution integral approach the mean resonance time of the stream flow. So the example is going to come from the simplest of our various watersheds. This is This is a catchment that is wet all the time, about 2,800 millimeters of annual rainfall. Soils usually within 10% of saturation. The slopes are very steep, maybe up to 45 degrees. It's the kind of quintessential headwater steep wet catchment. And here we have more impermeable bedrock than any other site where we've worked, 300 meters of firmly compacted conglomerate. So it's the closest thing to a watershed sitting on a parking lot as you will find. So watershed, we'll start with a very simple model, just 3 tunable parameters. So this is some of the work we've been doing with Kelly. And here we're simply taking an approach that uses the continuity equation to move water laterally downslope and into the stream. So we're solving mass balance in each pixel in terms of precip in, ET out, subsurface storm flow out, saturation overland flow if it develops in the lower foot slopes out, and then the input of subsurface storm flow from, say, the upslope cell. We're also going to look at residence time in this regard. Soil water residence time. The stream water residence time, using the convolution integral technique, we know to be about 4 months. Now, this number is highly uncertain as well, but I'm not going to talk about that so much today, but we need to think about measurement uncertainty just as much as our parameter and model uncertainty. But the stream water residence time is about 4 months. We can also compute the soil water residence time using the same technique, where we choose a system response function for the soil that allows us to compute the soil water residence time based on sampling that we might do weekly with a suction lysimeter. Now, it turns out that if we look at our map here of the catchment, if we look at the placement of these suction lysimeters, which were in different topographic positions, there's quite a strong relationship between simply distance from the divide, that is how far down slope one is, and the mean residence time of the soil water, going from about a week to maybe 160 days or thereabouts. So this is valuable information because now we're seeing that simply by looking at distance down slope, we can say something about the increase in residence time. Take that relationship and regionalize it at the catchment scale. So here's now a map of that same 3-hectare watershed. This is showing the stream outline. And now this black and white surface is a map of residence time going from, the range here is from about 3 weeks to 3 months, roughly. So we've simply taken that XY plot on the previous slide, and we've used that to regionalize residence time across the catchment. So now we have soil water residence time, and we have stream water residence time, and we have discharge as our tools to evaluate the model that we're saying are probing different types of information space. So let's run the model. Here's runoff on the y-axis, and here's measured and modeled. We're only looking at now runs with a Nash Sutcliffe efficiency of above 0.75. There's 1,750 of these runs that had values above 0.75, and here you're seeing the nature of that fit. Remember, this is a 3 tunable parameter model, so we're starting very, very simply. And here we're looking at it in log space just to show you where it's working well and where it's not. But what we're going to do is we're going to assume that this is acceptable. And we're going to now begin to think about the tracer component of this model that's achieved these good fits for runoff. And what we're going to do is add tracer to the model in the storm rainfall, so to the soil surface, and we're simply going to add the tracer component, or concentration, to the precipitation, to the discharge in and out of each cell, just like we did hydrometrically with that part of the model. And then we'll use the convolution integral approach to compute the soil water and stream water residence time, now using the outputs and the lagging and damping that we see expressed through the system. So here's an example of what I'm talking about. Here we added the tracer. This is a kind of a breakthrough experiment for that time series of flow data I showed earlier. So we're adding the tracer here. This is the pulsive tracer coming out of the system in this exponential-like way. The reason that we have these gray areas is that this is showing 1,750 runs, each with that Nash Sutcliffe above 0.75, so it's kind of like an envelope of breakthrough. And what the model is suggesting is that this directly simulated residence time over that prior parameter range from about 30 to 95 days. And this is then what we come up with this simple model, and this is what you saw earlier. With this 3-parameter model, we can do a great job at discharge efficiency, but we can't at the same time get residence time anywhere near right in terms of stream water residence time. We can begin to approach stream water residence times, but then we really do a poor job with this other axis, in this case, the stream discharge. Let's look at this another way. Here's the catchment now. So here's the time series of flow, which we do a very good job of. But now if we look at the soil water residence time, this is the modeled soil water residence time for this domain. Now the range in data is only 2 days. Very unrealistic based on what we computed from the suction lysimeter data. So we would reject that model, and because we recall that our range of soil water residence times was 0 days, maybe up towards the divide, or a week up near the divide, to about 120 days, increasing in the downslope direction. So what if we could then think about making the model more complex and maybe using the experimentalist to guide what complexity you add to the model to begin to get the right components of flow and mean residence time in a very simple way. So we're going to think about this same model exercise in a kind of a model rejection-like way, where the experimentalist is guiding the rejection. And we'll start with our model that we just looked at, this first model with 3 tunable parameters. We'll look at another model which has 4 parameters, 5 parameters, and 6 parameters. So what we'll do is look at these 4 models, the one you've already looked at here, Model 1, with 3 parameters. Model 2, we add a parameter by including effective porosity. Model 3, we add another parameter by adding an explicit unsaturated zone. And then Model 4 this does by looking at adding an explicit porosity or unsaturated zone term. We're going to delay or hang up some tracer and increase our residence times accordingly. And here's an example of what that might look like. You've seen this top 2 panels already. This is that same time series, and this is the ability to model the flow over that time period using first of all Model 1 with 3 parameters. Here's Model 2, Model 3, Model 4. All produce pretty good fits, and here we're looking at only the runs with efficiency measures above 0.7. We can add our virtual tracer Here's the one that you've already seen, Model 1. Now for Model 2, 3, and 4, you're seeing some of the effects now of here the effective porosity, here adding both effective porosity in the unsaturated zone. You're seeing really rather different tailing or breakthrough behavior as a result of those additional parameters in the model. So you're seeing different so-called late time behavior in the way in which the tracer is moving through the catchment. So what we're able to do is perhaps compare these models in terms of their ability to get at discharge, which I'm showing on the y-axis in each of these plots. This is a recent paper we have in WRO with Kelly Vacher. Stream water residence time here, and now we've just normalized our goodness measure from 0 to 1, and similarly for soil water residence time, normalizing our goodness measure from 0 to 1. The first model with the 3 tunable parameters that you saw already does a great job with discharge, but doesn't do well for stream water residence time or soil water residence time. Adding these parameters, the experimentalist can evaluate these additional parameters in terms of how it might ultimately move into his or her understanding of the basin behavior. And of course, where we want to be in this exercise is in the top right-hand quadrant, because this is giving results for the right reasons in terms of stream water residence time, soil water residence time, and discharge. So it's a way to think about how much detail might be warranted in the model from a very functional point of view, and we would argue that these are complementary measures for evaluating the model. Now, the last just couple of slides I wanted to report on were some quite encouraging findings from Kevin McGuire's PhD work here at Oregon State that Willem van Veersveld's following up on, and Chris Graham at the H.J. Andrews. This is a mesoscale watershed, about 60 or so square kilometers, and within it are a number of sub-watersheds. And Kevin looked at stream water residence time in each of these systems by collecting stream water data and precipitation data over 3 or 4 years that was completed recently. And this is another paper that came out in WR just a couple of months ago. But what we're really wanting to understand is what's the relationship between basin area and residence time? And if there's no relationship between basin area and stream water residence time, might there be some other metrics that explain the distribution of stream water residence time at the mesoscale? Because all I've shown you so far are these tiny headwater basins and soil water at the hillslope scale. Well, here are some of these data that Kevin has reported that are really quite encouraging. Here's mean residence time on the y-axis, and again, it's for these 6 catchments shown here. These are of different size, so the area varies from just 10 hectares to over 60 square kilometers, and it turns out that there is no relationship between catchment size or area of the catchment and its mean residence time. But if you look at some simple flow path measures, if you look at some simple topographic measures, like flow path length, like flow path gradient, or in this case, length over gradient, this is simply extracting from a DEM using a tool developed by McGlynn and Seibert last year in WRR. You can actually explain a lot of the variance of residence time just by knowing something of that catchment's topography. And this is an outgrowth of some of the PhD work of Brian McGlynn at MyMy some years back. So when we look at the length over gradient statistic, that's the mean of the flow path length divided by the mean of the flow path gradient extracted from each watershed. We can explain over 90% of the variance of mean residence time, albeit with some uncertainty in these estimates, which suggests, which in fact is here, is bounded by very small catchments here and here. This is watershed 10, a steep wet catchment with fairly low mean residence time, and this is watershed 8 with long mean residence time. And it says that in terms of the particle transport through the system, the large scale is the sum of the small scale. We've also speculated at what the slope of this line might mean if we think of these y-axis of mean residence time in units of time and the x-axis in units of length. This is something of a landscape scale conductivity. and we're also using this in our models. Of course, like the MIMAR example, we can now take that relationship and regionalize resonance times now over the mesoscale, and we're doing that in our modeling work currently. All right, so to sum up, and maybe look ahead a little bit, I think that we are really not much farther ahead than where we were when Dunn 83 wrote that paper in Journal Hydrology. I think that, like he noted, we still have this morass of process complexity that's been described by experimentalists in different hillslopes and catchments around the world. And we've done little to generalize. We've described, these unique characteristics of different basins, but we've not really done the intercomparison needed to begin to classify and come up with a typology of catchments. This is one of the 6 science themes of PUB that Ross Woods, Gunter Bloschel, and Mark Stiglitz are leading. And I'm confident that over the next few years we're going to see some watershed classification schemes. I know Dave Wallach and colleagues at USGS have come up with a national scheme, which is a great start. And another thing that's really striking is that there's really no formal protocol for gauging an ungauged basin. So in terms of what to do and what order and why, we have very little guidance from the literature in this regard, and this is probably one of the things that we really need to look into in the coming years. On the modeling side, I think we're guilty as a community of building over-parameterized models, and many speak to this question in papers that we read, not considering equifinality, the parameter uncertainty. But I guess from the experimentalist point of view, we've not done a lot to reject models. The first thing we might do is have a moratorium on acronyms. So no more acronyms for our models, because we don't want to hang on to that model, we want to reject it. Now, it's true we need models, and there are different purposes for different watershed models, but in a research way, I think we really should be focusing on rejection. And I don't think we've really considered as a community the value of these bits of soft data that the experimentalist might have from a catchment, or a farmer, or a local villager who might know something of some major flood event that can bound parameter ranges that we might be using in our estimates. I think the residence time is something that can be quantified with data. I think we're less than 6 months away from having tunable diode laser mass spectrometers that many of us will have in our labs. So no longer will isotope data be difficult to analyze or costly. These things will be on the order of $30,000, so bringing down the price of a mass spec by at least an order of magnitude. And preliminary efforts suggest that these data that can come from the laser mass spectrometers are very acceptable in terms of the precision and accuracy that we might need in catchment hydrology. So residence time, heterogeneity, and most importantly, like discharge, makes sense across all scales. It probes a different axis, I think, and it's non-redundant, and I think it makes a good system constraint. And maybe it's a way to think about how we might make a model more complex. And it perhaps finally is a way to bridge the gap between the scale of our traditional measurements and the scale of our physically based models. Thanks very much.
Well, thank you, Jeff. That was a really interesting talk. And at this point, let's go ahead and open it up for questions. Maria, are you there?
Ladies and gentlemen, if you wish to ask a question, press star followed by 1 on your touch-tone telephone. If your question has been answered or if you wish to withdraw the question, press star followed by 2. Press star 1 to begin.
Or you can type your questions in the chat box there.
You have a question from the line of Richard Hooper. Please proceed.
Hi, Judith. I guess just looking at your last slide, I have lots of questions. Let me start with your last slide. Isn't what you're really getting at is this is another kind of integrative measure at the catchment scale that we can use for our catchment models, as opposed to these internal measurements which we've been trying to use over the last maybe 10 years that are difficult to relate to the catchment scale? I mean, is there anything more profound than that? The fact that we would have a time series of input precip and output isotope concentrations, input and output. We can now use that, and we'll have the higher frequency that we can actually do
absolutely. I think you're hitting on a really important point. There was a paper that Stuart Franks wrote as part of his PhD with Keith Bevan back in the late 90s, where they were looking at different types of data that could be brought to bear for top model calibration. And they showed quite clearly that the integrated measures, like maybe the aerial expansion of surface saturation in the catchment, which was an integrated measure of the whole catchment groundwater response, that kind of information was infinitely more useful than a single groundwater well or a TDR probe or what have you.
Exactly.
So absolutely, I think that it's these integrated measures that are very important. And maybe the other thing that's important are patterns. You know, patterns of things that can be used in a model evaluation way, where we worry less about the precision of our measurements, but we try to get a complete kind of picture or map of the catchment, because those patterns could be, I think, in the future extremely valuable for evaluating our models.
Okay, and I guess just one last thing to leave with the group. I mean, this is exactly what we want to try to distill, one from a community level in terms of our quest for these investments from NSF, of saying these are the kinds of measurements, this is what's going to make the difference in our field. And it's getting to this sort of specificity, both what you talked about in terms of what we need from the modeling side or the informatics side more broadly, as well as what we need from the field side. So with that, I will sign off.
Again, ladies and gentlemen, to ask a question, press star followed by 1. You have a question from the line of Jan Obol. Please proceed.
Oh, hi, Jeff. Again, a very nice presentation.
Sorry, I can't hear you, Jan.
Oh, sorry. Can you hear me now?
Yes.
Okay, sorry. I just have a really short question about earlier on in your presentation you said we should not use topography for characterizing our hill slopes, but the Bedrock topography or something. And then later in the presentation you still use it for the characterization of your flow path. Are we running into trouble if we use either?
Sorry, I'm really having trouble hearing you, Jan.
I'll type it in then.
Okay. Maybe while Jan is doing that, if there's not another question right now, I could respond again to what Rick said. This was the last slide I didn't think I'd show, but perhaps I would in the context of what I might think are the big questions. And to me, it has nothing to do with the talk that I just gave. I think it has to do with the fact that in hydrology, we see network behavior at all scales, meaning that if you look at the pore scale, like this diagram from Kurt Roth at Heidelberg, we see network behavior. If you look at the plot scale from some of the work that Marcus Weiler and Hannes Flüeler have done at ETH, this is ubiquitous in terms of vertical flow through soil profiles using dye tracers to look at this kind of network-like behavior. Or you look at any river basin, we see network-like behavior in the channel. I think that our big challenge in a maybe not Kawashi, but as a field, is to say that these networks are at all scales. Our work at the hill slope scale and many other groups that were at the SLICE meeting suggest that while we often can't see these kinds of things like these purple lines in this field here, if this animation was to work, you would see from some of Marcus's modeling work, we can represent this behavior only when we consider the network-like properties of these hill slopes. So this kind of juxtaposition of matrix and fast flow. To me, this is the big question. This is something for which we have no theory currently. And if I was to think of things that might alter the way we really view watersheds, it would be maybe confronting and taking notice of the fact that this flies in the face of what we do typically with Darcy Richards as our subgrid parameterization. These networks, I think, are key for not only physical behavior, but again, the geochemical behavior and other things that we see. So I'll shut up and have a look at Jan's question here. John?
Yeah.
Duncan, should I read Jan's question? Or?
Yeah, sure, just in case somebody's not online.
Jeff, earlier in the presentation you mentioned not use topography to characterize hill slopes through bedrock topography. Later you showed a good relationship for length over gradient derived from topography. How do we marry the two? Geez, I wish Jan had cut out there a few minutes ago. It's a tough question. But I think maybe it's at the scale of individual hill slope. That's where the effects of the kind of fill and spill present themselves. At the larger scale, perhaps those influences begin to erase a little bit. But it's interesting that still, even at the mesoscale, soil depth variability seems to be key for getting at realistic residence times. We've been comparing soil depth-based estimates of residence time at the Andrews using some geomorphological mapping that the Forest Service has done, compared to, soil depth-based estimates of watershed volume using soil depth information against mean residence time-based estimates of watershed volume. So by that, I'm saying if we know the residence time and we know the flow, we can back out what the subsurface volume might be. And they correspond pretty well, and it suggests that in our models that are using residence time as an evaluation tool, getting at the spatial distribution of storage can be quite important. At the hill slope scale, one of the things that Marcus has had some success with is doing some detailed soil depth measurements and then knowing something of the mean variance and correlation length scale, generating stochastic representations of soil depth at the catchment scale, and then using that in the model. So treating it as a kind of a stochastic function. And I think for a long time, and it seems to be a useful approach for maybe getting at this kind of question that Jan is asking at our catchment scale.
Which I guess ties into the next question there from Penn State.
Yeah, I mean, soil depth and its distribution seems to be a first-order control on hill slope response. Increasingly, I think groups are reporting that as a really important type of data. A great example is in the Pacific Northwest, trying to understand cut bank seepage to forest roads. You'd think this is a simple problem. We have 500,000 miles of forest roads on federal land in the western U.S., something roughly like that. We have no tools to estimate where the roads will intercept lateral subsurface flow and where they won't. A lot of work going on now at various universities in the Northwest, regressing measurements of ditches and culverts and various topographic positions to all kinds of terrain statistics, and no one finding any good relationships between, say, topographic index, plan curvature, all these geomorphic relations you might develop with topography. I think a lot of this is just the result of subsurface topography influencing the local, appearance of flow at these road cuts. So maybe it's the grain at which you're looking at the system. Jan's question, I think, suggests that at the grain of 60 square kilometers, maybe the individual details of the bedrock topography aren't important, but the soil depth distribution in a kind of a statistical way is still important. But at the grain of a hill slope, I think that subsurface of this either fill and spill or just how it connects up these network-like features that we see that it seem to be so ubiquitous on the trenched hill slopes. I think we had 25 trenched hill slopes represented last week at the slice workshop, and all showed quite network-like behavior of one form or another.
And any other specific suggestions for how soil scientists can work with hydrologists, or what type of soft data could be used by you and your peers?
That question's for me, John?
Yeah.
Or the group in general?
That was to you specifically, but I'm sure others are welcome to chime in.
Yeah, I mean, if we had some soil information that could be used as a proxy for how frequently an area was inundated with water, so some kind of delaying modeling information that might say something about how we bound variable source area dynamics. Maybe something about transformations of nutrients in certain topographic positions, and if there's soil information that could be useful there. I think a lot of groups are trying to develop pedo transfer functions, which are trying to really use our soil information as almost hydrological variables in many ways. But from a personal point of view, I'd like the soil scientists to kind of weigh in on these lateral network-like features that we seem to be seeing on our trenched hill slopes, and maybe put them in the context of soil catenary sequences, or how these soils are developing in relation to in relation to these networks. When we go to our Pacific Rim sites, most of them are incredibly steep and wet. All are fairly stable where we've been working, but some might have really impermeable soil, and as a consequence of that, have developed some really complex and efficient preferential flow networks laterally on the hill slope. Maimai is a good example. Then we go to a site that looks almost identical at Fudoji in Japan or H.J. Andrews in Oregon, similar steep wet hill slope, but these are formed on volcanic soils and are really coarse permeable soils, no preferential flow networks. They don't evolve because the soil texture is such that there's not a driver maybe for developing or driving these networks. So it seems that there's potential way to come at this with theory in terms of why these networks might develop. And maybe it's not related to hydrology at all. Maybe it's thermodynamics or entropy generation, minimization or maximization, or maybe there are other theories or approaches that we could bring to bear in our catchment studies that are a bit more outside the realm of what we typically deal with, but could be, just what we need to confront some of these real paradoxes.
Okay. Any other questions? Maria, are there any in the queue?
None in the queue.
Okay. Well, Jeff, thanks again for a great talk. We really enjoyed it. And thanks, everyone, for dialing in. And we'll be back next Friday at 3 p.m. Eastern with Epi Fufila from NCEB. Thanks, everyone.
Thank you.
Thank you all for your participation in today's conference. This concludes today's presentation. You may now all disconnect. Enjoy your